So you'll recall from our last class that we showed you some accommodations for the use of a truth table where more than one Boolean operator was in the mix with two or more inputs. And here we have an OR. And so what I wanted to do was to share with you how this would look as a logic gate. So on Monday, we pretty much stuck to the software side of things. What do I mean by software side of things? When we're dealing with Boolean operators and their combinations, we create a Boolean function. And this is something that we can take into a programming environment and create in software. One of the realities of computer science and computer engineering is that computer engineering and hardware far outstrips the development and innovations. The rate of innovation far outstrips the innovations that are happening in the software development arena. Put another way, if you want to do something with logic, you can prototype in a software environment and you can actually embed that logical functionality in a software program. But if you have to take it to scale, and by scale, I mean you're supporting a user population that runs into the tens of thousands or hundreds of thousands or millions, as large corporations do, Amazon, Google, large government organizations. Basically, the trick is to take a functionality and translate that or port it over to the hardware side. Hardware implementations of the same function are often 100 or 1,000 times faster and more efficient in terms of performance. So what are we saying? There's an interplay between the world of software development and hardware engineering that's complementary. And oftentimes when we prototype, we take things to a software environment to try algorithms out. And there can be innovations in algorithms that are revolutionary, that are exceptions to the general comment I just shared. But on the whole, if you have something you need to take to scale where you're supporting many users with a function, it pays big dividends to take it to hardware. So if I take this, what kind of two input logic gate are we talking about here? OR is correct. So if I look at this drawing, it's a crude drawing. It is a crude drawing, and you have a sloped point that it's not a rounded point, so it looks more like a rifle bullet, but it's intentionally drawn so that it's obvious it's not rounded, okay? So this is what an OR logic gate with two inputs would look like. And you notice that the A and the B inputs on the left side, and then there's an out, right? So this was just something that I drew on the back of an envelope with a vis-a-vis marker, and I beamed this to myself. Now, what is this little triangle here? This little triangle is precisely the B bar. It's the differential or custom implementation of a NOT to a singular input, right? We're not applying the NOT to the output. We're not applying the NOT also to the A input. We're only applying the NOT, in this case, to the B input, which is why this triangle is, so this triangle represents the NOT logic gate. Put another way, you're looking at two logic gates. You're looking at an OR NOT, you're looking at an OR logic gate with an A and a B input, but then on the input side for the B, this is a smaller version of the NOT. A NOT is represented by a right pointing triangle with a single input and a single output. And we're parking it right at the base of the B input. Does everybody understand what I'm saying here?
Yes.
Yeah.
Okay. So this diagram is important for us to understand before we go into a software development environment. And it's important to understand before we start, it's helpful oftentimes to draw the logic gate, but sometimes it's better to take what we know here. And we've talked about the canonicals, right? So here are the resulting canonicals of this Boolean function. This is a very basic function. And by function, we mean that there's two or more Boolean operators in combination. Now, if it's the same operator, meaning we have ors that are fed into other ors, and it's just nothing but ors that are connected in a cascading fashion, like what's shown in your book, then that's not a function, that's still a Boolean operator, and it just has multiple inputs. So it's an OR with 3 inputs or 4 inputs or 5 inputs, and you're taking 2 input ORs and stringing them together. Does everybody know what I'm saying by that? Everybody knows what I'm talking about? We're taking the out of an OR, and this out feeds into the A of the next OR. And that allows us to have, just like here, the out of the first AND is fed into the top input of the second AND. And then we have, everybody see that?
Yeah.
Yeah.
Okay, so this isn't, we would not consider this to be a Boolean function or a complex logic gate. It's the same operator, it's the same logic gate. We just string them all together so that what we end up with is 3 inputs and a single out, and that's how we represent it. Now, I want to be intentional about explaining these two different diagrams. This is referred to as the interface diagram of a compound or complex logic gate. We could call this a compound logic gate because it uses multiple ANDs, but we wouldn't call it complex because we don't have a mix of different ones, right? So just to keep that terminology consistent, the interface diagram only shows the inputs and the outputs and the basic shape of the whole thing as a whole. The implementation diagram, on the other hand, shows an internal view of the inside components along with the inputs and the output. So this one is useful when we're stringing gates together. This one is useful when we're trying to understand the internals of that hardware component. Okay. Any questions about the difference between the interface diagram and the implementation diagram? Now, why make the distinction? Why should we care? Why don't we just use the implementation diagram all the time? Well, that gets busy. And essentially, you can have a logic gate that has multiple inputs. And again, when it's part of a larger hardware design, you don't want things to be so busy, it's hard to interpret. So there are cases where the interface diagram is preferred over the implementation diagram. And I hope that's crystal clear. So what I want to do is go back to, and let me update my roster now that we've got more people here. Let's just make sure we capture this. Any questions at this point? Does everybody understand the difference between a compound logic gate where we have multiples of the same thing versus a complex where we're mixing it up with 2 or more different ones, right? Let's get back to this. We have a diagram here. We have our canonical here. And one important thing we need to be able to do, another important and related skill, is to be able to take the simplest expression of a canonical. So we take the simplest case of a canonical expression, whether that's the standard or the reverse. Simple meaning shortest. So I don't want to create a logic statement with this. That's not the simplest case. For this table, The simplest case or simplest canonical expression is this. And what we want to do is add to this. So the logical expression, we're going to call this IE means that is. So whenever you see the initials IE, that's a Latin term that means that is, id est. But it's a common abbreviation to indicate the words that is. So whenever you see IE, I want you to substitute IE for that is. When I use EG, those are Latin abbreviations for exempli gratia or something like that. I may not be pronouncing Latin correctly, but it's a free example. So you're saying, for example, when you see EG, E period, G period, I'm saying, for example. It's just a shorthand way of, and you see this commonly in a lot of formal journal articles and research reports, right? People will say IE. That is pseudocode, right? So a logical statement is something you're very familiar with by now. It's pseudocode, right? So in this case, what is it we're going to do for this? How can we state this as an if, then, else logic statement? Well, I would say if A is equivalent to, what does the not mean?
0.
0 is correct. And I'm using a double equal sign because I want to indicate equivalence. If I use a single equal sign, that's the assignment operator, right? So I don't want to confuse people. I'm not going to say if A equals, because that in coding language, a single equal symbol is used as an assignment operator. So I'm going to do that. If A equals 0, and then I'm going to put a comma, equivalent to 0, B is what? What does this show?
1.
1.
1. 1. Right? Then out now, is that true? What kind of a canonical expression am I citing? Is it the standard canonical expression or the reverse?
The reverse.
It's the reverse. It's the reverse. So the reverse would be false cases, 0 outcome, right? So I have to put 0 here. If what's stored in A is 0 and what's stored in B is 1, then the output is going to be 0 else. Now, where you indent and how you do this is largely a style thing, right? So I could put else here, or I could, by convention, I could put it there. It all depends on what practice you're used to. Else out is equal to what? 1.
1.
1.
There you go. So that's pseudocode.
I have a question.
Yes.
Where you see where you put out equals 0, it should be 2 equal signs instead of 1.
Yes. You make a good point here because what we're doing in this logical statement of logic gate behavior, right? if we were taking this, so what we have here is a logical statement of the logic gate behavior. And what we're saying is that if what's stored in A is 0 and what's stored in B is 0, then when we execute the logic gate, what's stored in out is 0. It's kind of tricky because you may have output variables that store the output of a function. So when we're writing it here, we're going to put double equal signs to indicate equivalence. And this is a statement of how this thing behaves or operates. Now, if I were doing this in the programming language, then I would have a single. So I'm glad you asked that question, okay? When I take this logic and then I want to represent this in a programming language, in order for the code to work, I would have to assign 0 to out, right? Or I would assign, in every other case, 1 to out. So if what's stored in A and stored in B is 0 and 1, then, so if I were in Python or I were in Java or I were in C or I were in, take your pick, right? Visual C#, right? I was all, and you have all these rich programming languages and some are object oriented. As I'm writing the statements for the programming environment out, this would be a single this would be a single equal sign. I'm describing the behavior of the logic gate. So it's a slightly different context here, okay? I'm describing the behavior of how this hardware component operates or functions. So I don't think you're wrong using I mean, if it would help you to put a single equal sign there in your logic statement just to keep things straight in your own mind, that's okay. You're not wrong doing it either way, but essentially what we're saying is that what's stored in out is 0. Or what's stored in out is 1. And that's an important distinction to make because a lot of times the out variable ends up becoming the input of the next logic gate. So in coding, a lot of times when you have outputs and inputs and you have interim values or intermediate values, in a multi-step process, you're going to store a temporary value in a given variable, and then that variable becomes the input for the next function. Am I making sense?
Yeah.
Okay, so I don't want to get bogged down in the weeds, but I do want to answer your question as seriously as possible. The hardware definition language is not it's not programming statements. And that's why we take a slightly different approach when we're building a logical statement of the logic gate behavior. And once again, I'm not going to scold you or slap you on the wrist if you say, okay, well, but in the real world, when I take this to Python or Java, I don't want to get confused, right? I like to remain consistent because I just think it's easier if everybody practices the same convention this way. And once again, we're defining the logical behavior of a complex. This is complex, right? We have 2 or more. So we're defining the behavior in as brief a format. And I want you to understand that when you take it to the HDL environment, we're not writing programming statements that execute in a specific order. We're defining the behavior of the logic gate, its inputs and outputs, okay? So let's let me take this a little further, but let me ask before we do that. Did I answer your question?
Yeah, you did.
Okay. So if you feel more comfortable leaving a single equal sign here because you know that you're gonna go into a software development environment, that's the next step for you. And it's easier for you to just leave a single equal sign here so that you don't get messed up when you go and port this into software on the software side of the house. I'm not gonna consider it a demerit, right? But I do need everyone here in the initial condition to use equivalents. This first line, you have to use double equals, okay? And again, thank you for asking that question, because it speaks to the HDL statements. They're not coding statements. They define the behavior of the inputs and outputs, and their order and execution of the order of execution do not matter. And that's kind of weird. So when you get into let me show you what I'm talking about. So we have this here. And what I'm going to do is take an or and modify it to include a not, right? And then we're going to go ahead and build a not or, and that's what we could call this, except that it's a custom not or. I could call it nor, but if I called it nor, that implies that the not is right here. So if I apply a not to an or, so that regardless of what's happening with the inputs, it's flipping the output, then my placement of the not would be on the front side of the or. Put another way, my function wouldn't be this. Okay. My function would be this instead. So let's take a different case. And we're going to call this a universal. So this is a differential application. In other words, it's a custom application of NOR, right? We're going to call this a differential case. And I would call this, if I had to name this Boolean, this complex Boolean, it's not, if I'm building a logic gate with it, I would call the logic gate not or. Okay. Because I'm applying that not only to the single input. Let's see what it would be like if I were to take let's take a more common case. It's universally applied to the output. So if I were drawing that, I'd be parking the triangle coming off the end of this, and that gets busy. In small diagrams, they typically put a large black circle that's filled in right here. Because if you try to put a point on the end of this, it kind of alters the distinction of the output in a weird way. So by convention, instead of using a triangle here, I mean, sometimes they'll come out like a millimeter or so, and then they'll build another triangle in front. But there has to be some distance between the output of the OR and then, okay, now we're going to feed it into a not. To condense that and simplify it, they simply put a very large round black dot right here, and that signifies that the not is applied to the output instead of one or both inputs, okay? And the effect of that not is different when you put it on one or both inputs as opposed to just the output. It's, and you'll see that when we get in there. Any questions before we continue here? So I have a function, and it's the AB, right? Function. So far, so good. Looks the same, doesn't it? Doesn't it look the same as this? Right?
Yeah.
Yeah.
Yeah, looks the same. But now I'm going to do this. Now I'm going to ask you the question, is this the identical, is this equivalent, is this the same function as this? Conceptually, what do you think?
No.
It isn't. It isn't. Okay, we would call the universal application, we would call that another word for this, AKA, also known as NOR. Okay. Does everybody understand what I'm getting at here?
Yeah.
Yeah, those are subtle things, but profound things. It's a little thing, but oh my gosh, do you get a different result? Okay. And once again, you want to take the canonical, the simplest canonical expressions, and then build a logic gate behavior statement, right? Or pseudocode, so that, and if consistent with what you do going into a programming environment, if you're going to take that straight into a software development environment or a programming language, you could, if it helps again. But all right, so I'm gonna go into the HDL environment. So I'm going to go from here, and now I'm going to take this into our HDL simulation. I'm going to build this in hardware. Is everybody ready?
Yep.
Yeah.
Okay, so this is where the magic starts to happen, right? So we're going to go into our, where I have NAND to Tetris, and I'm going to go into my tools, and I'm going to go into my hardware simulator environment, and I'm going to right click and run this as administrator. And it's going to launch my hardware simulation environment. Now, one of the things that I want to share with you is that the built-in chips are a resource, and I have an OR in here already. So I'm going to take my OR, and one of the things that I want to share with you is that when you take the HDL example, right, if it doesn't show Notepad, if it doesn't show the Notepad icon, what I want you to do is I want you to open with, and then always use this app, and then look for more apps, and then find Notepad, right? And select Notepad, so that Notepad is always associated with an HDL file extension. Does everybody understand what I'm saying here?
Yeah.
Yeah. It's like how you did the when you were making the program.
Yeah, because otherwise, I mean, what it is a text file. And what we want to do is modify the text file. And I'm going to do this. Here's the thing. I want you to notice that this is a basic HDL file. And let's look at the NOT. Here is the NOT. It's very simple, right? So I have two different HDL files or definitions. I have one for NOT, and I have one for OR. And in the header, one of the things that you have to understand is that this this name here has to match the name of the HDL file. If there isn't a match between the HDL file name and this chip name right here, it'll barf. Okay. Now, this particular statement is commented out. So the 2 forward slashes, this is just header information and it's good to know. The forward slash asterisk and then the reverse asterisk forward slash is a way of stating the behavior logic. Okay. And over here you see out equals 1 if, see, and there are many different ways to state the logic. Our textbook authors, express the logical behavior in a very straightforward way. But you notice that inside here, when you're looking at, okay, the values for A and B inputs, they do use, for consistency purposes, this double equal, right? Because they want to say, okay, 1 is stored in A before you execute. So out is, out. All right, if out is assigned 1 if A is equivalent to 1 and B is equivalent to 1, 0 otherwise. So this is just their way of expressing the logic of any questions, the logical behavior, right? Now I like using like a pseudocode style logic expression because I can follow that more easily. And if I want to launch into a programming language, it's easier to do that. So my style is a little different. So I would have the slash asterisk asterisk slash, and then I'd say if blah blah blah, then else, right? And then everything in between the slash asterisk and the asterisk slash is just a multi-line comment instead of having to do double forward slashes for each line. But so I could put an asterisk here and then put no, I could take these out, right? Everybody understands what I'm saying, right? I could take these out and then I could have a slash, I could have a asterisk, I'm sorry, asterisk slash. I take this out. This is the same as double slash, double slash, double slash, line by line by line. Now I'm not going to do that. Oh, yeah, okay. So now it's going to get weird on me. I'm going to close this and open it. I don't save it. Yeah, all right. So there we are again. Everybody with me still?
Yeah.
So remember that the name of the HDL file has to match the name of the chip or it won't load. You'll get an error. And I'm going to create a custom chip called not or, and I'm going to take the logic of this and combine it so that I have 2 inputs. All right. So I'm going to go ahead and I'm going to modify this and I'm going to save it as, and I'm going to call this not or. And I'll even tweak this a little bit and make it 2 caps, right? Everybody with me?
Yes.
Now not or already exists, you want to replace it? No, I don't. See, I demonstrated this before. So what I'd like to do is open up my not or. This is not or. So I had not or text that I created. And what you see here is that I have a NOR gate out. This is the same logic. So out equals 1. Now this is for a NOR. Actually, this is for a case where the not is applied to the out of the or. So this version of not or is actually the same as this version of not or. okay? So the example I'm about to provide will be this example, all right? And we're almost there. I'm going to take this not or, and I'm going to change it. So I'll do a not or 2. But the thing I want you to understand is that the name of the original source, the source statements were saved as a text file, and then I changed it to an HDL extension so that the hardware simulation environment could interpret that. And that the name of the, so if I look at the HDL version of this, it's the same thing. All I did was rename it. So not or here for the HDL file name matches the chip name here. I'm going to go ahead and create a slightly different version of the chip. And what I'm going to get is different behavior. So instead of having this different logic statement and different behavior, the internal parts are going to be organized a little differently based on the logic statement. And in order to do that, I want to spend a little quality time working from the or and then modifying it, but then building it out differently. So how are we going to wrap this up in order to close out our class on time? This is what the HDL looks like when you have a universal implementation of not with or, and that creates a NOR logic gate. There's also a NAND logic gate. NOR and NAND are like very fundamental building blocks that you can use to build any kind of logic, any kind of hardware logic. And in fact, NAND and NOR are each used to build and or and not. So it's kind of a chicken and the egg conundrum. Remember that NAND and NOR are a bit like protons, neutrons, and electrons. And or and not are a bit like the elements of the periodic chart, where they're the basic building blocks. Your elements of the periodic chart in chemistry are the basic building blocks that are used to create compounds and mixtures that we work with every day. So you have this kind of a hierarchy of different components. The universal version of applying a not to the output of an or creates what's known as a NOR. But if you do something where it's a custom application to just an input, you really need to call it something different. And I'm going to call it not or. To avoid confusion, I'm going to change the name that I already had here so that it's NOR. And that way, yeah, I'll change it to NOR and NOR. I don't think I have, do I have a NOR? I have a NAND, I have a NOR and I don't have a NOR. So I'm going to change this to NOR and change it to NOR so that way I won't have a name conflict. Okay, is everybody with me?
Yes.
Yeah. So this was in a previous class that I did this. I'm going to save this as, and I'm going to call it NOR HDL. And then we're going to finish the simulation of the custom version at the start of our very next class. Okay. So this is NOR. I'm going to change this to NOR. And I'm going to, now I've got it all consistent. The name of the HDL file matches the name of the chip and the other reference where it's stored. And that's going to give me a way to distinguish this combination or this build. So when I show you the not or, we can understand that those two chips are distinctly different. And that's why you have to be careful with your naming conventions. If you're not careful about how you name and how you decide to build something, it creates an issue. Today's date is the 14th, right? And it's September. I've updated this. And I'm going to close this and save my changes. And we will pick up the implementation in HDL of the not or at the start of our next class. Are there any questions before we close today? Any questions?
No questions.
Okay. All right. We'll see you on Friday. Thank you for joining us. Please remember to complete your reconciliation before the end of the week so that we can post the second version of our Module 1 assessment so that you can log your final attempt of the Module 1 material. Okay. I'm going to stop sharing.